Hello, yes, so we can begin now. So, welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today, we are happy to have Yoshiki Uchida, and he's going to talk about SMEFT, HEFT, and beyond, introducing the broken phase EFT. I'll send you a reminder when 5 minutes are left.
Okay, so let me start. First of all, thank you for inviting me to such a nice seminar. And yes, today the topic is like this. And I'm the postdoc in the South China Normal University, and I will move to the Central China Normal University in Wuhan in the next month or this month as a postdoc. And this talk is based on this paper. Okay, so before we start, let me self-introduce. So I'm from Japan and I got a PhD at the Nagoya University in Japan. And yes, and my main interest is the Higgs phenomenology, effective field theory, dark matter physics, and extra dimension theory. And recently I wrote a paper about the asymmetric dark matter from the primordial black hole evaporation. So if you're interested in, please visit our paper. And for more detail, please visit my webpage shown here. Okay, so let me start today's talk. So today's talk is about the effective field theory. So let me start by introducing the two representative EFT composed of the standard model fields. And yes, please interrupt me anytime if you have some questions. And the first example, the first EFT is the standard model effective field theory, shortly SMEFT. And we show you the Higgs sector of the SMEFT here. And the symmetry is SU3 times SU2 cross U1, which is exactly the same as the standard model. And the field content is a standard model of fields before the electric symmetry breaking. I mean, Higgs doublet, SU2 gauge field, and U1 hypercharge gauge field, etc., etc. And the power counting is performed in terms of the 1 over lambda expansion. So this is the basics of the SMEFT. And the other example is HEFT, so-called Higgs effective field theory. And the symmetry is again SU3 times SU2 cross U1, but the SU2 cross U1 hypercharge is non-linearly realized in this case. And the field content is the standard model fields after the electric symmetry breaking. I mean 125 GeV Higgs boson, W boson, Z boson, massless photon, etc. And the power counting is in terms of the loop expansion. So before we enter the detail about the EFT, let me ask, what is a non-linearly realized symmetry in the HEFT? So this is a very important concept, very important things in the Higgs effective field theory. So what is a non-linearly realized symmetry? So let me begin by the simplest case example, which is the O4 symmetric scalar field model. And the Lagrange is given like this. And let's assume that because of the negative mass square, this scalar develops a wave. And usually we parameterize this phi. Phi is the fundamental representation under the O4 symmetry. And usually we parameterize this symmetric field phi as like this. Sigma is the fluctuation, physical fluctuation field, and the pi is the Gauss-Boson fields. And just simply substituting this expression into the original Lagrangian, we get the Lagrangian in a broken phase. So this is if we take the Cartesian coordinate. But let's take the polar coordinate. In this case, the sigma field is parameterizing the radial direction, while the Gauss-Boson parameterize the sphere angle. And yes, the Lagrangian is just substituting this expression into the original Lagrangian, and expression is like this. And XA is a broken generator, and the F is a vector, a unit vector directed to the wave direction. Okay, now let's assume that we don't know the UV theory. So, because let's assume that we live in the energy scale much lower than the breaking scale. So in this case, all we know is our world is O3 symmetric, and we can observe the three massless Goldstone boson and the one scalar field. So it sounds strange to have the Goldstone boson in the low energy. Let's gauge our theory, and in this case, we have the three massive gauge boson. And at this point, I wanted to emphasize that this situation is historically realized. I mean, this is exactly the same as the situation before the discovery of the Higgs boson. So before the discovery of the Higgs boson, we somehow know that SU2L times U1 hypercharge is spontaneously broken to the U1 element because we have the three massive gauge bosons. So people tried, but at that time, we don't know how the SU2 cross U1 is spontaneously broken to U1 hypercharged. So the people introduce Higgs doublet or just think about Higgsless theory, such as technicolor theory. So the situation is just like that. So in that case, how we proceed? So of course, we can take the effective field theory approach because we know that the theory is symmetric under the O3 and we know the representation under the O3 symmetry. We can write down all the O3 invariant operators. So in this case, we can ask one question such as, should we include these Goldstone-Boson interaction in the low energy EFT? So because Goldstone is the triplet under the O3 symmetry, these are obviously these operators are O3 invariant. But the answer is no. Uh, at least for the mass term, we should not write down the mass term because the Goldstone should be massless. And as for the 4-point and the 6-point interactions, basically naively we can include this interaction, but actually if we include this interaction, it describes massless scalar fields, not the Goldstone bosons. So let me ask another question. Should we write down this interaction? The answer is we should include this interaction because this interaction is already included in the let's say UV completed EFT original theory. So we should include these operators. So we can ask what are the criteria or principle for inclusion or exclusion. Sorry, inclusion or exclusion of the Goldstone interactions. And actually, this is a very important concept of the nonlinearly realized symmetry. So this is a very important statement. Sorry. Sorry. So this is a very important statement. If the symmetry O3 is realized due to the spontaneous symmetry breaking of the larger symmetry O4, then we should write invariant theory not under the O3 symmetry, but under the nonlinearly realized O4. So we still don't know what is the nonlinearly realized O4 symmetry, but let us assume this statement is correct. So somehow the O3 invariant EFT is not enough to describe the low energy theory, but we should write the O4 invariant theory. So maybe the next question we should ask is, what is the transformation law of the broken phase field, Goldstone and sigma field under the nonlinearly layers O4. So how the pi A Goldstone and the sigma field transforms under the nonlinearly layers O4? So naively, we can define this field transformation under the O4 by substituting this expression into the original transformation law. So G, blue colored G is the O4 transformation matrix. And if we substitute this expression in terms of the broken phase field into this transformation law, we can naively assign these transformations. So the transformation matrix G just pass through this sigma because sigma is a singlet field. But actually, we can also insert the arbitrary O3 matrix here because this F vector is directed to the wave direction. And because the wave is invariant under the O3 transformation, we can insert this O3 transformation matrix. But actually, this O3 transformation matrix H is necessary because if we don't insert this H, we cannot define the transformation law of the pi field, Goldstone-Boson field under the O4 symmetry. I mean, sorry, if we act this O4 transformation matrix G to the Goldstone matrix, basically the resulting matrix include not only the broken generator, but also the symmetric generator. So this H is necessary to eliminate this symmetric generator part. And and only after that, we can define the transformation law of the Goldstone-Boson field by just compare this matrix after the transformation and before the transformation. So this is nothing but the nonlinearly realized O4 symmetry. And we call this transformation, we call this symmetry as a nonlinearly realized symmetry because the Goldstone-Boson fields after the transformation, pi prime, is no longer the linear function of the pi before the transformation, but it is a nonlinear function of the pi. Sorry. So now you can see that this is the transformation law of the Goldstone-Boson fields, and it includes the constant shift by the wave. So this is why people called the Goldstone-Boson has a shift symmetry. Okay, so now the thing is clear. So let's assume we don't know the UV theory. So now writing the O3 invariant theory at low energy is not enough, but write the nonlinearly realized O4 symmetric Lagrangian, and the each fields transform under this nonlinearly realized O4 like this. So because of the shift transformation, this shift symmetry of the Goldstone-Boson field, now the pi 4-point interaction or 6-point interaction is obviously forbidden. And allowed Lagrangian is like this. And now F sigma is F sigma and V sigma is the arbitrary function of sigma. And because this sigma is singlet under the nonlinearly realized O4. And if we replace this sigma by the observed Higgs boson H, it is just the Higgs effective field theory. So this is a concept of the Higgs effective field theory and nonlinear realized symmetry. Okay, so if there's no problem, I think we can proceed the broken phase EFT uh, about our new effective field theory. Okay. Okay. So this is a recent situation about the standard model of effective field theory and the Higgs effective field theory. So recently, we people assume some specific UV model and matched this specific UV model onto the SMEFT or HEFT and compare these effective field theories. And there's also the bottom-up approach here. And yes, also the general discussion here. And today, in today's talk, we focus on the type 2 system model. And because in my mind, the type 2 system model is very interesting. I mean, the new scalars wave in the type 2 system model must be much smaller than the electric scale. So in order to avoid the low parameter constraint, the triplet wave must be much smaller than the electric scale. So that's why we focus on the type 2 system model. And this is, in this table, I summarize the good point and bad point in the standard model effective field theory and the Higgs effective field theory. So, how to say, good thing in the SMEFT is easy to handle, but the disadvantage is the SMEFT is only applicable if the cutoff scale is much larger than the electric scale. As for the HFT, it is applicable even in the cutoff scale is a little bit closer to the electric scale. And the disadvantage is the HFT is not easy to handle because as I showed in the previous slides, the Goldstone boson transforms non-linearly. So the interaction basically includes the infinite power of the Goldstone bosons interactions. So now we can suggest the alternative effective field theory overcoming the shortcoming of both EFTs, which is so-called broken phase effective field theory. We suggest in this paper. And these three items are the concept of the broken phase effective field theory. So, uh, so for example, if we introduce a new scalar field S and it develops a wave, then basically the physical scalar field, I mean, the mass eigenstate of the physical scalar field is linear combination of the H and S tilde. So in our broken phase effective field theory, we first take these fields into the mass eigenstate, and then integrate the heavy fields in the mass eigenstate in the broken phase. I mean, S tilde prime. And this is just like the HEFT. And then after that, we take the unitarity gauge. This means we just substitute U equal 1. So this eliminates the complexity of the Higgs effective field theory because in the theory, there's no longer the Goldstone boson. There's no Goldstone boson anymore. So the third concept is a little bit technical, but when we integrate the heavy fields, just like S tilde prime here, basically we solve the equation motion with respect to the S tilde prime and substitute the solution of the S tilde prime into the original Lagrangian and get the low energy effective field theory. This is what we call integrate out at the tree level. Sorry. So, but in our effective field theory, basically this is the equation of motion, and if we try to solve this equation of motion with respect to the S tilde prime, basically we in the usual EFT we expand S tilde prime and coefficient. This is the parameter in the original Lagrangian in terms of the 1 over m square. But in our broken phase effective field theory, we only expand the heavy field with respect to 1 over m square. Capital M is the mass of the heavy field, capital S, but not for the parameter C. So this is our broken phase effective field theory. So now let's perform matching on the types system model on the broken phase effective field theory and SMEFT and compare these two effective field theories. So in this talk, we focus on the types system model. And this is a brief introduction of the types system model. And in this model, in order to realize the tiny neutrino mass, we introduce a triplet scalar field delta, which is triplet under the SU2L. And neutrino mass is generated by the lepton number violating interactions like this. And yes, as I mentioned before, the triplet wave must be much small compared to the electric scale in order to avoid the low parameter constraint. And this is the status of the doubly charged Higgs boson mass. And yes, because we assume the smaller wave, then it is corresponding to this region. And basically the doubly charged Higgs boson mass is around larger than the 400 GeV. And from now on, we perform the double expansion with respect to the epsilon, and epsilon is the ratio of the triplet wave and the electroweak scale. And also 1 over m delta. M delta is the mass of the triplet field delta. So this is a strategy. So we first perform matching onto the broken phase effective field theory. So in this case, we first apply the electric symmetry breaking. Then the types system model is rewritten in terms of the broken phase field. And after that, we can bring these scalar fields into the mass eigenstate. And after that, we integrate as a heavy mass eigenstate fields, these 6 fields. Then we get the broken phase effective field theory. And the other approach is that we first match types system model onto SMEFT by integrating out its user triplet field delta. And after that, we substitute the wave and apply the electric symmetry breaking. Then we get the standard model effective field theory after the electric symmetry breaking. So we compare these two effective field theories. So first, we perform the matching onto the broken phase effective field theory. So one difficulty is that in the broken phase effective field theory, in the broken phase, there are so many fields to be integrated out. If we consider the SMEFT, then we can just integrate as the SU to triplet delta. But in the broken phase, there are so many mass eigenstate scalar fields. So we must integrate these fields one by one. So, but we can solve these difficulties by considering the Z2 symmetry in the original UV Lagrangian. So this is the scalar potential of the types system model. And these two interactions, U1 violating, U1 lepton number violating interactions. And we can easily see that this whole of the Lagrange is invariant under this hypothetical Z2 symmetry. We call this as a hypothetical Z2 symmetry because under this Z2, not only the scalar field, but also the parameter is transformed. And after the electroweak symmetry breaking, this symmetry is still hold uh, under under this form. So this suggests that the solution of the equation motion for the heavy scalar field, phi heavy is the heavy scalar field to be integrated out. So this is this odd. So uh, this odd field must be proportional to the this odd parameter. So this symmetry makes integrating out much simpler. Okay. So maybe I think we still have the 5 minutes, so I can show you the numerical evaluation.
Yes, sure, sure.
Okay. So this is a numerical evaluation between the broken phase effective field theory and the broken phase SMEFT. So this is a benchmark, and as you can see, the broken phase effective field theory can describe the UV theory much accurately. So this blue dotted line is calculated by the broken phase SMEFT. And so this lambda minus is the linear combination of the parameter in the original Lagrangian. So yes, if we take the lambda minus as a larger value, then the deviation is become much larger because this is 10 to the 3 and this is 10 to the 2. So so in this case, if we take the lambda minus as a larger value, then the deviation between these two effective field theory become much larger. So this is yes, and R delta is the ratio of the electroweak scale over the triplet mass. So this is the same figure, but the horizontal axis is now epsilon. Epsilon is the wave ratio between the triplet wave and the electroweak scale. And yes, even in this case, we can see that the broken phase effective field theory is much describes the UV theory much accurately than the broken phase SMEFT. Okay, so in this last slide, I will describe why the broken phase effective field theory is much better than the SMEFT. So in the broken phase effective field theory, there is one-to-one correspondence between the Type's seesaw model and the broken phase EFT. I mean, so for example, there is a diagram in the UV theory that is mediated by the heavy field H plus minus. And in the broken phase effective field theory, there is also always there's always a corresponding diagram. And so this UV diagram is replaced by these three diagrams. So UV and the BFT have the one-to-one correspondence in the diagram level. But because the SMEFT treats the heavy scalar fields as one multiplet, which is the SU2 triplet delta, so we cannot take into account the scalar mixing as the lower order of the perturbation. So in the broken phase SMEFT, there's only the three diagram, and this diagram is only described by this single diagram. So yes, so in this broken phase effective field theory, this H0 mediated diagram and H plus minus mediated diagram is described by only one diagram like this. So this is why the broken phase effective field theory is much better than the SMEFT. So this is a summary. And we suggest the alternative effective P theory overcoming the shortcomings of the both SMEFT and HEFT. And we match type 2 system model onto SMEFT and broken phase effective P theory and examine if HEFT more accurately reproduces the UV theory. And we performed the numerical calculations and found that BFT reproduces the UV theory more accurately than the SMEFT in the regime that the triplet wave, the electric scale is much closer to the triplet mass. Okay,